Hello. So let me begin this lecture by summarizing what we did last time. And the first thing that we talked about is how does a source of EMF works? How does a common battery work? We said that the job of an EMF is to supply energy to the rest of the circuit. One thing I repeatedly want to point out, electromotive force or EMF is not a force. What it does is to raise the energy of the positive charge carriers by taking them from a lower potential to a higher potential, and the amount of work that the EMF does is the EMF multiplied by the current that it provides. The EMF is measured in volts and I is of course in amperes. Then we gave you a method of calculating potential difference as you go along a circuit. So, potential drop as you go along a circuit. So, what we said is, if you move in the direction of current flow, there is a drop in potential as you cross a resistor. For example, if this is the situation, this is the positive end and this is the negative end. So, what will happen is this, the current is flowing like this, then let us call this A, let us call this B. Then what we said is, the potential at the point A is more than the potential at the point B by an amount I times R. That is, if you are going along the direction of current, then the potential drops as you go along, and of course the reverse is true. If you move in the direction in which the electrons actually move, which is opposite to the direction of current, the potential will of course rise as you cross a potential resistance. The amount of energy that a resistor absorbs from the source of EMF is given by I square R, and that is equal to V square over R. So, this you have to be careful. This V is the potential drop or potential difference between the ends of the resistor, not the EMF, the potential supplied by the source of EMF, but this is the potential difference across the ends of the resistor. And this is of course valid for ohmic resistances, and this is what we are going to be talking about most of the time. Towards the end of the last lecture, we pointed out that resistances are major cause of power loss as you move along a transmission line. See, what actually happens is, usually the generating stations are far away from the consuming stations, and typically the towns, cities and villages, they would be consuming electricity, and the power would be of course generated elsewhere. Now suppose P is the power to be delivered from a generating station to a receiving station, and let us suppose there are cables which have resistance R on the way. So, resistances of cables which carry such currents, then the power dissipated, which let us call it power dissipated in cable, is given by I square RC, and since I is P by V, so it is P square by V square into RC, and that is because power is nothing but current times the voltage in which it is supplied. So, what you need to do if you want to reduce your power loss is to supply the power at a fairly high voltage. Now, but that causes a serious security concern because it can damage or be a source of hazard. Now, incidentally, though we are talking about the direct current transmission, this is also true of alternating current transmission or AC transmission, about which we might be talking about at a later stage. But one of the advantages of AC transmission is you can build transformers which either step up or step down. So, you could supply at high voltage and at the receiver's end reduce it there. Now, of course, this facility is not available for DC transmission. So, you have to build send it on lower voltage, but build booster stations on the way. However, the AC transmission suffers from serious disadvantages, and we will be talking about them later, and particularly long distance transmissions always takes place by DC over thousands of kilometers, and usually they are by undersea cables. So, anyway, this is one of the points that we should remember about it. So, we discussed the source of the fact that the resistances absorb power from the source of supply. So, let us look at an example. So, consider for example a circuit in which I have a current which is given to be 1.6 ampere going in this direction, and there is a resistance of 20 ohms on the way. So, let me call this end A, this end B, and in this section of the circuit there is a source of EMF, but I am putting a question mark there because, so let me write it, it is an EMF source with no internal resistance. So, the idea is this, that what is given is when 1.6 amperes of current passes in this direction, this section of the circuit AC, the section AC absorbs 64 watts of power. This is the data which is given. My job is to find out this how much of power is absorbed by this one. Not only that, what is the polarity of the source of EMF, supposing it is a battery, which side is the positive terminal and which side is the negative terminal. Now, VAC is power which is 64 watts divided by the current which has been given to be 1.6 amperes. So, it's 64 divided by 1.6, which is equal to 40 volts. And likewise, VAB. Now, since this is just a resistance which is equal to I times R, and I is 1.6, R is 20 ohms, so that's equal to 32 volts. Now, this immediately tells me that since the potential difference between the point A and C is 40 volts, and that between A and B is 32 volts. Now, direction of the current has been shown so that the point where it is entering in is at a higher potential. So, therefore, the voltage provided by the battery is 8 volts. Now, notice that the section AB, that is the resistance, absorbs I square R amount of power, which is 1.6 square into 20, which is equal to 16 square is 2.56 multiplied by 20, that's equal to 51.2 watts. But the total amount of power that the section AB has absorbed is 64. So the power absorbed by the battery is 64 minus 51.2 equal to 12.8 watts. Now notice one thing, this is the amount of power flowing into the battery. Now which is consistent with the fact that I had obtained that the battery is supplying an 8 volt and the current I is 1.6 amperes. So therefore 1.6 into 8 is 12.8 as it ought to be. More importantly, since the battery is absorbing power, that is, power is flowing into it, the side of the battery which is towards the point A should be positive, that terminal should be positive, so that in effect what is happening is the battery is getting charged. Since we have been talking about power, let's just do a small calculation that suppose, just to give you an idea of how much is this power. We frequently at home and particularly in offices, we are very negligent in switching off power when we don't need it. But let's look at some idea about how much power we might be wasting if we are careless. Now suppose I have a 100-watt bulb. And let's suppose you are going on a vacation and by mistake you forgot to switch it off for a period of 1 month. So this was kept switched on for 1 month, let's say 30 days. Now let's look at how much money you would be actually wasting if you do that. Let me take a very conservative price. I will assume that each household unit of electricity costs 3 rupees. What it means is it costs you 3 rupees per kilowatt hour. This implies that if you put on a 1000-watt bulb for 1 hour, you would be wasting essentially 3 rupees. But let's see. One of the things that we know is this, that in India, the household power supply takes place between 220 to 240 volts. Let me take 240 for convenience. So what we are given is V square over R, where R is the resistance of the bulb, is given to be 100. V square is 2, let me take V to be equal to 240. So that is 57600 divided by R or divided by 100 is equal to R. So which means R is equal to 576 ohms. So what is also given is I times V is 100. So the current that we are talking about is 100 divided by V. So it is 100 divided by 240. So let's keep it at 5 by 12 ampere. So what we have said is this, that I have kept 100 watts per 10 hours. So what it means is per day, which is 24 hours, I am consuming 2.4 units of electricity. Which works out to 30 days, 72 units per month. Units meaning kilowatt hour. At a conservative estimate of 3 rupees, it is rupees 260 per month you will be wasting. Of course, nowadays incandescent bulb of the type that I discussed are going out of fashion, giving way to new bulbs, low wattage bulbs, which are either LCD or LED bulbs, which consume much less power but have better luminescence. But the purpose was not so much to point out the amount of money that you lose, but to tell you that given power and the voltage, how to calculate data like the resistance of a bulb, the current that is flowing through it, etc. Continuing with our idea of bulb, let me give another example. Suppose we are given two bulbs. So, two bulbs, one of power 60 watt and the another of power 90 watts. And they are to be put in 240 mains. Now, there are two ways in which I can put it. One of them is called series combination, where you put the two resistances end to end. So, this is series combination, about which we will be talking about in this lecture in detail. So, it is this, that is R1 and this is R2, and this is the potential difference across them is 240. And we have said already what is the power rating of the bulb. Now, when we say power rating of the bulb is 60 watts, what it means is, if you connect it across the line supply, which I have taken to be 240 volts, that is the amount of power it will consume. In other words, for the first bulb P1, I have V square over R1. So, this means 60 is equal to 240 square divided by R1. So, solve for R1, it is 57600 divided by 60, so which is equal to 960 ohms. Likewise, the second bulb, which is V square over R2 equal to 90, that will lead to a similar calculation, R2 equal to 640 ohms. So, what we have said is this, that which combination, this is the series combination, which combination will dissipate more power? Basically, a series combination means that the same current is flowing through both. They are in a section of a circuit in which the same current is flowing. So, therefore, according to what we have learned, we have said when they are in series combination, the drop across R1, so total drop V is equal to, supposing current is I, which is the same throughout, so that will be equal to I R1 across the first resistor plus another term I R2 across the second resistor, which will lead to the current being given by V divided by R1 plus R2. add them up. So it is 240. If you add it up, it is 1600. So that's equal to 3 by 20 amperes. So that is one of the combinations. And let's also calculate how much is my V1 and how much is my V2. So my V1 is 3 by 20, which is the current, times R1. So 3 by 20 multiplied by 960. So that's equal to 144 volts. And V2 will have a much lower one, the same 3 by 20 into R2, and R2 was smaller, and this turns out to be 96 volts. If you add up these two, you will of course get 240 as is expected. So what we are having is this, that the power dissipated by the first bulb is equal to I square O times R1. So I was 3 by 20, so it is 9 by 400 multiplied by 960, that was the resistance. So if you do this calculation, it works out to 21.6 watts. And a similar calculation, P2, will give you 14.4 watts. So total power dissipated will be 21.6 plus 14.4 equal to 36 watts. So this is what happens in a series combination when you put them one to n. There is another type of combination possible, and that is known as a parallel combination. I will be dealing with both of them in detail in this lecture. So basically the definition of parallel combination, it is very important that you understand what is parallel combination, because very frequently one believes that because the circuit looks parallel, it is a parallel combination. That is not really true. We will give you examples of circuit which looks parallel but is not really a parallel combination. But so what is the definition of a parallel combination? Two resistances are supposed to be in parallel combination if the potential difference across both the resistors happens to be the same. So potential difference or voltage across the resistance are the same. Remember, in series combination what we have said is the current that is flowing through both the resistances are the same. So that is the actual difference between a series combination and a parallel combination. Okay, so let us look at what type of combination we are talking about. So the combination is like this. Supposing this is my supply, 240 volts as we said. Now what we do is to connect it like this. So this is R1 and this is R2. So you notice that the potential difference between this pair of points is the same as the potential difference between this pair of points, because this or this is connected to this side of the battery, this or this is connected to that side of the battery. So this is what actually happens. So therefore, my voltage is the same. Therefore, my current will be different because the resistances are different. So let's look at how much is the current I1. So current I1 then is, since the potential difference is 240, so this divided by my R1 was calculated to be 960, so this is 960, that's equal to 1 by 4 ampere. and I2 is 240 divided by R2, which was shown to be 640. So that's equal to 3 by 8 ampere. Now let's look at how much power is consumed in each. So this one clearly consumes I1 square R1. So power 1 is I1 square R1, and that's equal to 1 over 16, 1/4 square, times 960, and that's equal to 60 watts. And P2, as you might expect, I2 square R2, well, I1 is same as I2 is 3 by 8, so it is 9 by 64 multiplied by 640, that's equal to 90. But you remember that our power ratings were supposed to be 60 watts and 90 watts, which means if you connected them across a 240 volt terminal, then this is what would be the power. So this sort of works out. So therefore, the total power consumed in this combination is essentially obtained by adding up the rated power. So total power consumed is 150 watts. Recall that in the series combination, the amount of power that is consumed was only 36 watts. So it turns out that the parallel combination, supposing these were bulbs, and particularly these are very important when you use them in decorative lighting like Christmas lighting or Diwali lighting, we use several strands of the wires which are in parallel combination, and within each strand the bulbs are placed in a series combination. As we have pointed out that within a strand, bulbs being in series combination, of course, reduces effective brightness that a bulb could deliver, but the power expense becomes much less. So having discussed the series and the parallel combinations, let us spend a little more time in trying to understand resistances in series and parallel. So we will be discussing resistances in series and parallel, but let me start with the little more complicated one. So resistances in parallel. So as I said that we define a parallel combination by this relationship, that the potential drop across them, okay, is the same. Now what is the effect of that? Let me draw a picture. So this is a point A, this is one of the resistances, this is another resistance. So this is R1, this is R2, and this end is B. So what happens is this, that supposing you want to go from the point A to the point B, this is the point where the potential drop, maybe it's connected to a battery source, so it's known. Now then you can take one of the many possible paths. In this particular example, you could go like this, have the drop of potential across that, come back and come back here. Alternatively, you can take this path also. In this case, there are two paths, but in principle, there could be similar arrangement. They look parallel, but that's not the full story. So when I apply a potential difference across AB, the same potential difference appears across all the resistors which are in parallel combination. So let's write down, when a potential difference is applied across the combination that is from A to B. The same potential difference appears across each branch. So I ask a question, what is the effective resistance or equivalent resistance? What is meant by equivalent resistance? The equivalent resistance is, supposing this entire circuit that I have here, this combination, I am to replace by a single resistance, then the current that is leaving A or entering B remains the same. Now remember, when I had the branches, there is a current coming in, but then the current divides into two. And in fact, in this simple case, you can realize, because current is nothing but rate of change of charge, so whatever charge is coming in, it is being divided into two parts. So therefore, if the current on this is I1, the current on this is I2, then of course I expect I to be, this is I, to be equal to I1 plus I2. This is just a continuity of current. So by equivalent resistance I mean, what should be the resistance with which I should replace this circuit such that the value of I remains the same. So effective resistance or equivalent resistance means, so a single resistance which can replace the combination such that I remains the same. Now let us look at this in a little more detail. Notice one thing, supposing delta V is the potential drop across any of these resistances, because I have said if they are in parallel, so let me emphasize here, I am looking at parallel combination in this section. If they are in parallel, then delta V remains the same whether I am on this branch or on this branch. Since delta V is the same, my current I1 is clearly delta V by R1 and current I2 is delta V by R2. So therefore, my current I equal to I1 plus I2, that is delta V by R1 plus delta V by R2. So if I take delta V common, it is 1 over R1 plus 1 over R2. Supposing my equivalent resistance was Req, then I should have been, because I said I remains the same, so it should be delta V divided by R equivalent. So if you compare this expression with that expression, you get 1 over R equivalent is equal to 1 over R1 plus 1 over R2. That is the standard formula for the parallel combination. Now I can easily extend the same thing to multiple resistances, more than 2, because the principle is the same, that potential drop across each resistance remains the same. So all that will happen is, supposing I have got R1, R2, R3, etc., the current in each branch will be given by delta V by I1, delta V by R1, delta V by R2, etc. And as a result, my equivalent resistance for more than 2 situation would be 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, etc., or which means a series 1 over M, 1 over R. I leave it to you to show that the value of Req is smaller than the smallest resistance in the circuit. So Req is smaller than the smallest resistance in the circuit. So let us look at now series combination. Recall I told you a while back that series combination simply means that the same current flows through each component circuit. Look at a situation like this, that of course the simplest is I have point A connected to a resistance R1, point another resistance R2, like this. I can have any number of them, this is B. As long as the same current is flowing through this, as we go through various resistances, it is a series combination. As a result, the potential drop across AB, so if let us call this delta V, this is sum of potential drop across this one, this is delta V1, and potential drop across this delta V2, and likewise this will be true for any number of them. So my delta V is delta V1 plus delta V2, which is equal to IR1 plus IR2, because same current passes through all of them. So it is I times R1 plus R2. But if you have to replace this combination by a single resistor, then the corresponding equivalent resistance would be simply this much. So Req in this case is R1 plus R2, and if I have n number of them, then I have sum over I, Ri, I equal to 112. But before I quit this discussion, let me point out something. Supposing I give you a situation like this. Now if you look at this diagram, it seems like parallel. There are parallel lines connected. But you look at it, that if there is a current flowing through them, it will be the same current which is flowing through. So this is actually an example of a series resistance. not parallel. Now, since I have already obtained the relationship for the series and the parallel combination, let me try to expand my scope a little bit and try to see how do they behave if I have combined situation. It is not very difficult. Let me take a very simple circuit. Suppose this is a point A, this is a point B, and this is a point C. Now look at this circuit. This is a combination of a parallel and a series combination. So let me call this an example. So suppose a current I leaves the point A. Now of course, since it is just passing through a resistance here, so current I would flow through this resistance, which is, let us call it R1. So the potential difference VAB is given by the potential drop in this case is I times R1. Now once it comes here, meets the parallel combination, then of course the current gets divided, but the potential drop between these 2 points remains the same. So therefore VBC is equal to, now you see this is I1, this is I2, because I know that the currents are different. Let us suppose this is R2, this is R3, but I have already told you that if the current in this section is I, and this is true of this section also, then this entire section you can replace by an equivalent resistance, which is given by 1 over Req equal to 1 over R2 plus 1 over R3. So this is the potential drop across VC is I times the R equivalent of this section, but R equivalent of this section is R2 R3 by R2 plus R3. That is because 1 over Req is 1 over R2 plus 1 over R3, so therefore Req is that. Now, so what happens to VAC? So VAC is obviously VAB plus VBC, potential drop across this plus the potential drop across that. So if I add it up, this is I times R1, which was already there, plus I times R2 R3 by R2 plus R3. So the current can be obtained immediately if VAC is known to us, supposing it is equal to V, let us keep it as VAC, divided by R1 plus R2 R3 by R2 plus R3. You can simplify that, and that will give you VAC times R2 plus R3 divided by R1 R2 plus R2 R3 plus R3 R1. What I will do now is, for the rest of this lecture, I will give some illustrative examples of the way one calculates the problems connected with series and parallel combinations. So let us proceed with some typical simple ones, and then we will gradually come to more complicated. So let me start with a problem of this type, example. So suppose I have a circuit like this. There is a battery here which is 8 volts, let us take. So this R1, let it be 2 ohms. This is R2, which is also equal to 2 ohms. R3 equal to 3 ohms. So let's number them. Let's call this A, this point B, this point C, this point D. How does one solve such a problem? Now, the first thing to know is, in many of these circuits, you will find it easy to first observe what type of combination do I have, and to try to reduce this circuit gradually into simpler and simpler circuits. Of course, this is not a complicated circuit anyway, but nevertheless try to understand this. So one of the things that you realize is this, that see, when I have plain wires without any resistances, there is no potential drop. The reason is, the connecting wires are always assumed to be resistanceless, no resistance. If there is no resistance, there is no potential drop. So which means that this point and that point will be at the same potential. Likewise, this point and that point would be at the same potential. Now remember that A and B will not be at the same potential, because in going from A to B, you will have to cross a resistance. But since the potential drop across R2 is the same as the potential drop across CD, that is potential drop across R3, by our definition of a parallel combination, R2 and R3 are parallel. Now if R2 and R3 is parallel, so let me write it, R2 is parallel to R3. Not because in this diagram they are looking parallel, but because the potential drop across their ends happens to be the same. This is important to realize. The definition of a parallel combination is that different components of parallel combination have the same potential drop across each component, and this is what I observe first. Now once I know that it's a parallel combination, I can replace that parallel combination by an equivalent resistance. So what is that equivalent resistance? Equivalent resistance of R2 with R3. That is, Req is equal to R2 R3 divided by R2 plus R3. And in this particular example, R2 is 2, this is 3, so 2 into 3 divided by 2 plus 3, so that's equal to 6 by 5 ohms. So this circuit is the same as this circuit. This is R1, which is equal to 2 ohms, and I replace R2 and R3 by a single resistance of this type. Let's call this Req, and that's equal to 6 by 5 ohms, and this was 8 volts. Now notice, this circuit has become very simple, because R1 and Req, they are in series, because the same current is flowing through them. So therefore, R1 in series with Req, so the effective or the new equivalent resistance is simply 2 plus 6 by 5, which is 16 by 5. So what it means is, this circuit is finally replaced by a circuit which has only a battery and a resistor. So I have an 8 volt battery, and a resistance which I have calculated just now to be 16 by 5 ohms. So the current is immediately calculated, that is the current supplied by the battery is immediately calculated, which is equal to 8 divided by 16 by 5, which is simply equal to 2.5 amperes. So I have already found out that the current that is being supplied by the battery is 2.5 ohms. Let us return back to our original picture. Now, if this battery is supplying a current of 2.5 ampere, my question then is, how much is the potential difference across AB? And notice one thing, the point A is at a lower potential than the positive end of the battery. That is because the current is going like this and we are dropping the potential by I times R1. And how much is I times R1? The I times I is 2.5 into 2. So therefore, what we find is that there is a voltage drop of 5 volt as you go from here to there, which means this point A, if I take this point to be at 8 volts plus 8, this point then is at 8 minus 5, that is equal to 3 volts. Now, the point B is connected to this, since this is my reference potential with respect to which I have taken the plus to be equal to 8. So this is also at the same 0 potential. So therefore, VAB, which is same as VCD. So let us write it down. VAB is equal to 8 minus 5, which is equal to 3 volts, which is also equal to VCD in my picture. So let us return back to the figure again. So this is 3 volt difference, this is also a 3 volt difference. So my current in this section of the circuit is 3 volts divided by 3, which is equal to 1 ampere. The current in this section of the circuit, because the potential drop is between these 2 points is 3 volts, so 3 divided by 2, that is equal to 1.5 amperes. Now notice this, that my current I was 2.5 amperes. So therefore, 2.5 ampere gets split into 1.5 ampere and 1 ampere. We will later on generalize this idea to situations where there are more than 2 branches and see that we have certain laws which are in place. Let me give you a little more difficult example. So let me look at this circuit. So let us call this R1, let us call this R2. I take this battery to 21 volts, this has 4 ohms, this has 8 ohms. In parallel with it, well, looking parallel at least, I have R3 which is taken to be 12 ohms and R4 which is taken to be 8 ohms again, and I connect them. But my circuit has little more complication. There is a switch here. So supposing my switch is open as is being shown here. Now this problem is very similar to the problem which we just now did. So what I have is that before the switch is closed, so this part of the circuit is immaterial. So, I have R3 and R4 in series and R1 and R2 in series. So, R3 and R4 in series gives me 12 plus 8 equal to 20. So, this will be equivalent to the following circuit. So, let me write down here before switch is closed. R1 and R2, they give me an equivalent resistance of 12 ohms because 4 plus 8. And R3 and R4 gives me 20 ohms, that is 8 plus 12. But then 12 ohms and 20 ohms are in parallel. So, the equivalent resistance Req is 20 into 12 divided by 20 plus 12. That is equal to 7.5 ohms. This is 21, and you can calculate the current, which is 21 volts divided by 7.5, which is equal to 2.8 amperes. Point is, this is what happens when this switch is open. Now, we would like to know what happens when this switch is closed. The entire nature of that circuit changes. I do not have time to do it in this lecture, but in the next lecture, I will take up the same problem and try to see what happens when the switch is closed. So, in this lecture, what we have done is to basically point out two major types of connection that you have in electric circuits, namely series combination and parallel combination. What we pointed out is that combination of resistances in series is defined by the fact that as you go through various components which are in series, the current flowing through each one of them will be identical. Parallel combination, on the other hand, has many branches and the current in each branch is different, but what remains the same is potential drop across each of the members of the combination remains the same. And this is the way, and not by the visual picture of a parallel, that you define what is a parallel combination. We will continue and explore more about series and parallel combination in the next lecture.